In November of 2022, a small team of physicists ran an experiment on a quantum computer and produced a result so strange that the journal publishing it took the unusual step of trying to describe, on the cover, in plain language, what had actually happened, because the technical paper alone risked being misread as something it wasn't, and misunderstood as something it also, in its own quiet way, actually was. Pale blue drift. The experiment took place on one of Google's quantum processors, a chip containing dozens of quantum bits, or qubits, each one able to exist, unlike an ordinary computer bit locked into a simple 0 or 1, in a delicate mixture of both states simultaneously. Researchers used this processor to simulate a specific, simplified mathematical system, and when they examined how information moved through that simulation, the behavior matched, with real mathematical precision, the predicted behavior of something entirely different, something that had never actually been built or observed anywhere in the physical universe. A wormhole, not a hole in space you could fly a ship through. A specific, carefully defined mathematical structure that, according to one of the more startling ideas in modern theoretical physics, might be secretly, mathematically identical to a very different kind of system entirely, a tangled, correlated arrangement of particles connected through quantum entanglement. That single sentence, quantum entanglement might be mathematically identical to a wormhole, is worth sitting with for a moment before we go any further, because it sits at the center of one of the strangest, most actively debated ideas in physics today, an idea researchers now refer to informally by the shorthand ER equals EPR, and understanding why anyone takes it seriously requires understanding two things that, on the surface, look like they belong to entirely separate branches of physics. The first of these two things comes from Albert Einstein's general theory of relativity, published in 1915, the same theory that reshaped our understanding of gravity as the bending of space and time itself, rather than a simple force acting at a distance. In 1935, Einstein, working with a colleague named Nathan Rosen, discovered something buried inside the mathematics of his own theory, a solution describing a bridge connecting two distant, otherwise separate regions of space and time, a tunnel through the geometry of the universe itself. This mathematical object came to be known as an Einstein-Rosen bridge, and in later popular science writing, it acquired the more familiar name most people know it by today, a wormhole. For decades, physicists treated this mathematical curiosity mostly as exactly that, a curiosity, a solution to Einstein's equations that seemed to require exotic, almost certainly impossible physical conditions to actually exist, and which, even if it somehow did exist, appeared to be so unstable that it would collapse and seal itself shut faster than anything could ever hope to pass through it. Wormholes remained, for most of the 20th century, a fascinating piece of mathematics with essentially no expected connection to anything actually observable in the real, physical universe. The second piece of this puzzle comes from an entirely different corner of physics, quantum mechanics, and specifically from a paper Einstein wrote, remarkably, in that very same year, 1935, alongside two other colleagues, Boris Podolsky and Nathan Rosen, the same Rosen who had worked with him on the wormhole solution only months earlier. This second paper had nothing to do with gravity or the geometry of space. It was an argument, intended by Einstein as a serious criticism of quantum mechanics itself, pointing out a deeply strange consequence of the theory that Einstein found genuinely uncomfortable, a phenomenon where two particles, once they interact and become what physicists call entangled, continue to share a connected, correlated fate no matter how far apart they later travel, such that measuring a property of one particle instantly determines the corresponding property of the other, even if that other particle is sitting on the opposite side of the galaxy. Einstein considered this apparent instant correlation deeply troubling, since it seemed to violate his own theory of relativity's insistence that nothing, including information, can travel faster than the speed of light. He referred to it, dismissively, as spooky action at a distance, and the paper describing it, now known simply as the EPR paper, after the initials of its three authors, was intended as a serious challenge to quantum theory's completeness, an argument that something essential must still be missing from the theory if it truly predicted something this strange. For nearly 30 years, the EPR paper remained largely a philosophical argument, difficult to test directly with the technology available at the time. That changed in 1964, when a physicist named John Stuart Bell developed a mathematical framework, now known as Bell's theorem, capable of actually distinguishing, through real physical experiment, whether entangled particles were genuinely, instantaneously correlated in the strange way quantum mechanics predicted, or whether some hidden, more conventional explanation, some shared property the particles had secretly agreed upon in advance, could account for the correlation instead, without requiring anything as strange as spooky action at a distance. Beginning in the 1970s and continuing with steadily improving precision through the following decades, physicists carried out this test, again and again, closing loophole after loophole that skeptics had proposed might explain away the results through some more mundane mechanism. Each successive experiment came back with the same answer: quantum mechanics was right. Einstein's discomfort, as it turned out, described something genuinely, physically real about the universe, not a flaw in the theory that some deeper, more comfortable explanation would eventually resolve. In 2022, this decades-long experimental effort was formally recognized with the Nobel Prize in Physics, awarded jointly to three physicists whose work, spanning from the 1970s into the 2000s, had progressively closed every remaining loophole and confirmed, beyond any reasonable scientific doubt, that entanglement really does connect particles in a way that has no equivalent anywhere in classical, everyday physics. So there the story sat for decades, two of Einstein's own 1935 papers, published only months apart, describing what appeared to be two completely unrelated pieces of physics. One described a strange, exotic bridge connecting distant regions of spacetime, a consequence of gravity. The other described a strange, uncomfortable correlation connecting distant particles, a consequence of quantum mechanics. Wormholes belong to the world of the very large, the geometry of space and time itself. Entanglement belonged to the world of the very small, the behavior of individual particles. For most of the 20th century, nobody seriously proposed that these two strange phenomena, sitting on opposite ends of physics, might actually be the same thing, wearing two different mathematical disguises. That began to change around 2013, when the physicists Juan Maldacena and Leonard Susskind published a paper proposing exactly this connection, formally, mathematically, arguing that a wormhole connecting two black holes might be precisely, mathematically equivalent to a pair of black holes that had become quantum entangled with each other. Two seemingly different descriptions of the exact same underlying physical situation, the geometry of a bridge through spacetime on one side of the equation, and the quantum correlation of entangled particles on the other, both describing, it turned out, the very same thing. This proposal became known, informally, by that shorthand mentioned earlier, ER equals EPR, directly referencing both of Einstein's 1935 papers, joined together nearly 80 years later into a single, startling idea. That idea, proposed as a genuinely serious theoretical conjecture rather than mere speculation, sat for years primarily as a subject of mathematical study, discussed and refined among theoretical physicists working at the intersection of gravity and quantum information, an active, respected area of research, but one that seemed permanently confined to pen, paper, and abstract argument, since actually testing it would require building and manipulating a real, physical wormhole. An experiment about as far outside the reach of any laboratory on Earth as an experiment could possibly be. This is precisely where quantum computers entered the story, and it's worth understanding exactly why a quantum computer, of all things, turned out to be the tool capable of making any progress at all on a question this exotic. An ordinary computer, no matter how powerful, struggles enormously to simulate quantum systems, because the number of variables needed to describe even a modestly sized collection of entangled particles grows so explosively fast that classical computers quickly run out of memory and processing power long before they can model anything resembling a genuinely complex quantum system. A quantum computer, by contrast, is built from the very same strange quantum ingredients, qubits capable of existing in superposition, connected to each other through the very same entanglement Einstein once found so troubling, meaning it can, in principle, directly simulate other quantum systems using its own native quantum behavior rather than attempting the impossibly resource-intensive task of faking that behavior with ordinary classical bits. The specific team working on the 2022 experiment, led by physicist Maria Spyropoulou working alongside Google's quantum computing researchers, recognized that if the ER equals EPR conjecture were correct, a sufficiently simplified, carefully constructed quantum system, built entirely from entangled qubits on an ordinary quantum processor, should behave, mathematically, exactly the way a wormhole is predicted to behave, even though no actual spacetime geometry, no actual gravity, and certainly nothing resembling an exotic tunnel through space was physically present anywhere inside the chip itself. The wormhole, if it appeared at all, would appear only in the mathematics, a kind of holographic shadow cast by the quantum system's own internal structure, rather than as any literal physical opening in space. This distinction matters enormously, and the research team, along with the journal that published their results, went to considerable, explicit lengths to make sure it wasn't lost in translation once the story reached a wider audience. Nobody built a wormhole. Nobody sent anything through a tunnel in spacetime. What the team actually did was construct, on Google's quantum processor, a highly simplified system of entangled qubits specifically designed to model, as faithfully as the technology currently allows, one side of the ER equals EPR equivalence, the entanglement side, and then carefully checked whether the resulting behavior matched the mathematical predictions physicists had already worked out on paper for what a simple, corresponding wormhole should do. It did. When the researchers encoded a small piece of information into one side of their entangled qubit system, and then applied a specific sequence of operations, informally described in the accompanying research as something resembling a negative energy pulse, the kind of exotic condition theoretical physics suggests would be necessary to hold a real wormhole open long enough for something to pass through it. The encoded information reappeared, intact, on the opposite side of the system, following a pattern of behavior that matched, point for point, the mathematical signature predicted for information traversing an actual wormhole, according to the equations describing that side of the ER equals EPR relationship. When the researchers ran a modified version of the experiment without that specific negative energy analog pulse applied, the information failed to reappear on the other side, exactly as the wormhole mathematics predicted it should fail to, if the bridge weren't held open properly. It's worth pausing on the specific size and simplicity of this experiment, because it matters directly to how the result should honestly be understood. The wormhole simulated inside Google's quantum processor involved just 9 qubits, an almost absurdly small, drastically simplified stand-in for the kind of system theoretical physicists actually study when working through the full mathematics of the ER equals EPR conjecture, which typically involves systems far too large and far too complex for any currently existing quantum computer to simulate faithfully. Researchers deliberately engineered this small-scale model, using a technique that allowed them to preserve the specific mathematical signature of wormhole-like behavior while discarding an enormous amount of the underlying complexity a genuinely complete, realistic model would require. essentially building the smallest, simplest possible toy version of the phenomenon capable of still exhibiting its key, defining behavior. This is precisely why the physics community's reaction to the experiment, once the initial wave of dramatic headlines settled, became considerably more nuanced and more carefully qualified than the excited framing many news outlets initially ran with. Several prominent physicists, including some who study quantum gravity and the ER equals EPR conjecture directly, publicly cautioned that describing the experiment as creating or observing a wormhole risked significantly overstating what had actually been demonstrated. What the experiment genuinely, rigorously showed was that a specific, carefully engineered quantum system reproduces a specific, narrow slice of the mathematical, behavior-theoretical physicists predict a wormhole should exhibit, under the assumption that the ER equals EPR conjecture is correct in the first place. It did not prove that conjecture true. It demonstrated that a real physical quantum processor, built from ordinary superconducting circuits sitting in a laboratory in California, could be coaxed into behaving, in this narrow, specific mathematical sense, the way an entirely different, far more exotic gravitational object is predicted to behave, a genuinely remarkable technical achievement in its own right, without necessarily settling the deeper theoretical question of whether entanglement and spacetime geometry are truly, fundamentally, the same underlying phenomenon. That careful, qualified framing doesn't make the result any less significant. If anything, it points towards something arguably more interesting than the simpler, more dramatic headline version of the story, because it demonstrates a genuinely new kind of scientific tool becoming available for the very first time: the ability to use a quantum computer not simply to solve practical computational problems, the application most people associate with this technology, but to directly, physically probe deep, unresolved theoretical questions about the fundamental relationship between quantum mechanics and gravity, questions that have, for the better part of a century, remained almost entirely confined to pen, paper, and mathematical argument, with no available laboratory technique capable of testing them directly at all. That new tool, and the specific, narrow demonstration it just produced, sits at the leading edge of a considerably larger, considerably stranger story about what quantum computers have been quietly revealing about the nature of reality over the past several years. A story that reaches well beyond this single wormhole-adjacent experiment, into a broader pattern researchers across multiple, entirely separate branches of physics have started noticing, one strange result after another, each one chipping away, in its own specific way, at the comfortable, intuitive picture of the universe most of us carry around without ever seriously questioning it. One of the strangest entries in that pattern doesn't involve wormholes or entangled black holes at all. It involves something considerably more modest sounding: a beam of light and a screen, an experiment so simple in its basic construction that a determined hobbyist could build a working version of it on a kitchen table, and yet so persistently, stubbornly strange in what it actually reveals about the universe that physicists have been arguing over its implications for more than a century, arguments that quantum computers have only recently begun to sharpen rather than resolve. The experiment traces back to 1801, when the English scientist Thomas Young shone a beam of light through two narrow, closely spaced slits cut into an otherwise opaque barrier, and observed the pattern that light produced on a screen positioned behind it. If light behaved simply as a stream of individual particles, you would expect two bright bands to appear on the screen, one directly behind each slit, the simple, straightforward shadow pattern any ordinary particle passing through an opening should produce. Instead, Young observed something else entirely: a whole series of alternating bright and dark bands, a pattern known as interference, exactly the kind of pattern produced when two overlapping waves, rather than two streams of particles, pass through the slits simultaneously, their peaks and troughs reinforcing each other in some places and canceling each other out in others. This result helped settle, for well over a century, a long-running debate about the fundamental nature of light, appearing to confirm decisively that light behaves as a wave rather than a stream of particles. Then, in the early 20th century, an entirely different set of experiments, involving the way light interacts with metal surfaces in what's called the photoelectric effect, work Einstein himself contributed to in a paper that would eventually earn him his only Nobel Prize, demonstrated with equal certainty that light also behaves, under different circumstances, exactly like a stream of individual particles, later named photons. Light, it turned out, according to the best available evidence, was somehow, simultaneously, both a wave and a particle, a genuinely uncomfortable conclusion that would eventually become one of the founding puzzles of quantum mechanics itself. The double-slit experiment became considerably stranger still, once physicists gained the technical ability, decades later, to send individual particles through the apparatus one at a time, rather than a continuous beam containing countless particles simultaneously. If particles were simply tiny, discrete objects behaving like miniature bullets, sending them through one at a time, with long gaps between each individual particle, should eliminate any possibility of interference entirely, since there would be no second particle present at the same moment for the first one to interfere with. Each particle should simply pass through one slit or the other and land on the screen, gradually building up, over many repetitions, that same simple two-band pattern expected from ordinary particles behaving like tiny bullets. That is not what happens. When physicists send individual particles through a double-slit apparatus one at a time, patiently allowing each one to complete its journey before releasing the next, the interference pattern still gradually emerges, building up dot by dot on the detector screen, each individual particle landing at a specific, seemingly random point. But the overall accumulated pattern, once enough individual particles have passed through, still forms the same alternating bands of interference observed when countless particles pass through simultaneously as a continuous beam. Somehow, each individual particle appears to be interfering with itself, behaving, in some genuinely strange sense, the mathematics of quantum mechanics describes with total precision, but no one has ever managed to make fully intuitive, as though it passes through both slits at once, rather than committing to one path or the other the way any ordinary, everyday object obviously would. This alone would already be strange enough to sustain an entire evening's conversation, but the experiment takes one further, genuinely unsettling turn, once physicists add instruments capable of detecting, directly, which specific slit each individual particle actually passes through. The moment researchers install a detector at the slits themselves, capable of recording, with certainty, which of the two openings a given particle traveled through, the interference pattern vanishes entirely, replaced immediately by the simple, ordinary two-band pattern you'd expect from tiny, discrete bullets passing cleanly through one slit or the other. Simply observing, measuring, gathering information about which path each particle actually took appears to fundamentally change the particle's behavior, collapsing whatever strange, wave-like, both paths at once condition it had been in into the ordinary, single-path behavior everyday objects display. Physicists refer to this collapse, this apparent transition from a strange, undetermined wave-like condition into a definite, particle-like outcome the moment measurement occurs, as wave function collapse, and it sits at the very heart of one of the deepest, longest-running, and still genuinely unresolved disagreements in all of physics. A disagreement over what measurement itself actually means, physically, at the deepest level, and why the simple act of gathering information about a quantum system appears to fundamentally alter that system's behavior in a way nothing in classical, everyday physics prepares you to expect. An even stranger variant of this experiment, developed decades later and known as the delayed choice quantum eraser, pushes this puzzle into territory that feels, on first encounter, almost impossible to accept as genuine, rigorously tested physics rather than some kind of trick or misunderstanding. In this version of the experiment, researchers arrange the apparatus so that the decision about whether to gather which path information, the decision that determines whether the interference pattern appears or vanishes, is made after the particle has already, apparently, passed through the slits and been recorded, striking a preliminary detector, its fate seemingly already sealed. And yet, when researchers later choose, based on a second, delayed measurement, whether to erase or preserve the which path information associated with that already recorded particle, the final pattern that emerges, once all the data is properly sorted and compared, still depends on that later choice, as though the particle's earlier behavior had somehow been retroactively determined by a decision made after it had already, apparently, completed its journey. It is critically important, and worth stating with real precision, exactly what this experiment does and does not demonstrate, because the delayed choice quantum eraser has become one of the most frequently misunderstood and most frequently overstated results in all of popular physics communication. It does not allow information to travel backward in time in any way that could be used to send a message to the past, or change a decision that has already been made, a possibility that would violate causality in a way physics has never once observed happening anywhere, under any circumstances. What it demonstrates instead is something subtler, and arguably even stranger once you sit with it properly, that quantum systems do not actually possess a single, definite history in the way classical, everyday objects do, until the full experiment, including every measurement relevant to it, has been completed, and the results properly correlated with each other. The particle was never secretly taking one path or the other the entire time, waiting for us to catch up and figure out which one. It existed, throughout the entire experiment, in a genuinely undetermined condition that only becomes meaningful, only resolves into something you could accurately call a definite history, once every relevant measurement has actually been made and the full pattern of correlations examined together. This is precisely where quantum computers have begun offering physicists a genuinely new way to explore this century-old puzzle, moving beyond simply repeating variations of the same basic double-slit apparatus, and instead building highly controllable, precisely programmable quantum systems capable of testing the deepest assumptions behind wave function collapse directly, under conditions no traditional optics laboratory could ever achieve. A quantum computer's individual qubits are, at their core, exactly the kind of quantum system the double-slit experiment probes, capable of existing in superposition, a genuine mixture of multiple states simultaneously, right up until the moment they are measured, at which point they collapse into one definite outcome or another, following probabilities dictated with total precision by the same underlying mathematics governing every version of the double-slit experiment ever performed. Because researchers can control every aspect of a quantum computer's qubits with extraordinary precision, adjusting exactly when and how measurements occur, entangling qubits with each other in carefully designed configurations, and repeating experiments millions of times in rapid succession to build up detailed statistical pictures of the results, quantum computers have become genuinely valuable laboratories for testing increasingly sophisticated, increasingly precise variations of exactly the kind of measurement puzzle the delayed choice quantum eraser first raised decades earlier using individual photons and carefully arranged mirrors and beam splitters. Several research groups have used quantum processors specifically to test more elaborate versions of these measurement puzzles, involving larger numbers of entangled qubits arranged in configurations that would be extraordinarily difficult, or in some cases essentially impossible, to construct using traditional optical equipment alone. One particularly significant thread of this research has focused on testing something called contextuality, a deeper, more general version of the strangeness-Bell's theorem first revealed about entangled particles, one that applies even to individual quantum systems that aren't entangled with anything else at all. Contextuality describes a genuinely strange property quantum systems display, where the outcome of a specific measurement can depend, in ways that have no equivalent in classical physics, on which other, entirely separate measurements happen to be performed alongside it, as though the quantum system itself doesn't possess fixed, independent properties waiting to be discovered, but instead generates its properties, in some meaningful sense, only in the specific context of whatever full set of measurements is actually being performed around it. Testing contextuality rigorously requires precisely controlling and measuring multiple quantum properties simultaneously, across carefully designed sequences of measurements, exactly the kind of controlled, repeatable, highly precise experimental environment a quantum computer is uniquely well suited to provide. Several experiments run on quantum processors over the past several years have confirmed, with increasingly tight statistical precision, that quantum systems genuinely do display this contextual behavior, closing loopholes that earlier, less controllable experimental setups had left open. Adding yet another layer of confirmed strangeness to the already considerable pile of confirmed strangeness quantum mechanics has produced, since Young first shone his beam of light through two narrow slits in 1801. This same underlying capability, precise, repeatable control over delicate quantum states, is also directly responsible for a separate, related story that made international headlines back in 2019. A story often referred to as quantum supremacy, or in more recent, slightly softened terminology, many researchers now prefer quantum advantage. In that year, Google researchers announced that their quantum processor, a chip called Sycamore, had completed a highly specific, carefully chosen computational task in approximately 200 seconds. A task the team estimated would have required roughly 10,000 years for the world's most powerful conventional supercomputer to complete using the best classical algorithms available at the time. The specific task itself was, admittedly, somewhat contrived, deliberately chosen, because it happened to align extremely well with the particular strengths of quantum computation, while being extremely difficult for classical computers to simulate. Rather than representing some immediately useful, practical computation with obvious real-world application. Sycamore's 53 qubits were made to execute a specific, complex sequence of random operations, and the processor's task was simply to sample from the resulting, extraordinarily complicated probability distribution describing the likely outcomes of that sequence. A distribution so intricate that simulating it classically requires tracking an amount of information that grows explosively, doubling with every additional qubit added to the system, quickly outstripping the memory and processing capacity of even the largest classical supercomputers on Earth. The announcement was met with genuine excitement throughout the physics and computer science communities, alongside immediate, appropriately rigorous scrutiny from researchers at competing institutions and companies. IBM, a major competitor in quantum computing research, published a detailed technical rebuttal within days of Google's announcement, arguing that with sufficiently clever classical algorithms and access to enough conventional storage capacity, a classical supercomputer could actually complete the same task in a matter of days rather than the 10,000 years Google's original estimate suggested, a considerably narrower gap than the initial headlines implied, though still one representing a genuine, substantial quantum advantage over the best available classical methods. That back and forth, an initial dramatic claim followed by serious, technically rigorous pushback, followed by refined, more carefully qualified claims from the original research team, is worth understanding as the genuinely normal, healthy texture of how significant claims in this field actually get tested and refined, rather than as evidence that the original result was somehow illegitimate. Google's team and other research groups working on similar demonstrations in subsequent years have continued refining and repeating these experiments with steadily improving processors and steadily more rigorous methodology, and the overall trajectory of the field's results, even accounting for the ongoing, healthy scientific debate over exactly how large any specific quantum advantage genuinely is, points in one consistent direction. Quantum processors are becoming capable of performing certain very specific, carefully chosen categories of computation that classical computers, no matter how powerful, structurally cannot keep pace with, not because classical computers aren't fast enough in some ordinary sense, but because the fundamental mathematics of simulating a genuinely quantum system, one exhibiting real superposition and real entanglement across dozens or hundreds of qubits, requires computational resources that grow so explosively with each additional qubit that no conceivable improvement in ordinary, classical computing technology could ever realistically catch up. This raw computational power, the ability to genuinely, faithfully represent and manipulate systems exhibiting real quantum superposition and real quantum entanglement, is precisely what connects this entire story back to everything discussed earlier tonight: the wormhole-adjacent experiment, the ongoing investigation into contextuality, and the deep, unresolved puzzle first raised by Young's simple beam of light passing through two narrow slits more than 2 centuries ago. A quantum computer isn't simply a faster ordinary computer built from smaller, more exotic components. It is, in a very real, physically direct sense, a small, carefully controlled piece of the same strange quantum reality the double-slit experiment first revealed, deliberately built and precisely manipulated specifically, so that physicists no longer need to rely entirely on delicate optical equipment and individual photons to probe the deepest, strangest features of that reality. They can now, increasingly, simply build the strangeness directly, qubit by qubit, and study it under laboratory conditions with a level of control that would have seemed like pure fantasy to the physicists who first began arguing over what these results actually meant, back in the opening decades of the 20th century. Nowhere has this deliberate construction of strangeness proven more directly useful, or more directly revealing about the actual texture of quantum reality, than in the unglamorous, deeply technical work of trying to keep a quantum computer's fragile qubits intact long enough to actually compute anything useful at all, a challenge that has forced physicists to confront, in extraordinarily precise, hands-on detail, exactly how and why the strange superposed multiple possibilities at once behavior of the quantum world gives way, so reliably and so completely, to the single, definite, ordinary reality we actually experience in everyday life. This challenge goes by the name decoherence, and it sits at the very center of both the practical engineering problem quantum computer builders face every single day, and the deepest theoretical question quantum mechanics has struggled with since its earliest years. A single, well-isolated qubit can maintain its delicate superposition, existing genuinely in a mixture of multiple states simultaneously, for a meaningful stretch of time under the right laboratory conditions. But the moment that qubit interacts, even slightly, with its surrounding environment, a stray photon bouncing off it, a tiny fluctuation in electromagnetic field from nearby equipment, even the faint, unavoidable thermal vibration of the atoms making up its own supporting structure, that interaction effectively constitutes a kind of measurement. In the same fundamental sense, the double-slit experiment's path detectors constitute a measurement, and the qubit's delicate superposition collapses, rapidly, irreversibly, into an ordinary, definite state, exactly the way the interference pattern vanishes the moment researchers install a witch path detector at the slits. This is precisely why building a working quantum computer is so staggeringly difficult, and why the field has taken decades longer to reach its current, still relatively modest scale than early, more optimistic predictions from the 1990s and early 2000s suggested it would. Every single qubit in a quantum processor must be isolated as thoroughly as human engineering currently allows, from literally every unwanted interaction with its surrounding environment, cooled to temperatures colder than deep space itself, shielded from stray electromagnetic radiation, and protected from even the faintest mechanical vibration, because any leak of information into the surrounding environment, however small, however seemingly insignificant, effectively constitutes an unwanted measurement, destroying the very superposition the entire computation depends on. Decoherence, in other words, isn't simply an engineering nuisance quantum computer builders happen to be stuck dealing with. It's the direct, hands-on, laboratory demonstration of exactly why the everyday world you and I actually experience looks and behaves the way it does, solid, definite, populated by objects that are either here or there, rather than smeared out across multiple simultaneous possibilities, the way individual, carefully isolated quantum particles can be. Ordinary, everyday objects, a chair, a coffee cup, your own body, are constantly, unavoidably interacting with their surrounding environment, countless trillions of tiny interactions every single second, each one effectively constituting a measurement, collapsing any potential quantum weirdness almost instantaneously, long before it could ever become large enough or persistent enough for anyone to actually notice. The strange, superposed quantum world isn't hiding somewhere separate from the ordinary, everyday world you experience. According to decoherence theory, it's happening constantly, everywhere, all the time, at the smallest scales, simply collapsing into ordinary definiteness so rapidly and so completely, due to the sheer, overwhelming density of environmental interactions any large object experiences, that it never has any practical opportunity to display its underlying strangeness at a scale large enough for human senses to directly perceive. Understanding decoherence this precisely, hands-on, through the daily, practical work of trying to prevent it inside a working quantum processor, has given physicists an unusually direct, unusually concrete window into one of the oldest, most contentious debates in the entire history of quantum mechanics: the question of what measurement actually is, physically, and what happens in genuine physical reality. To all those other possibilities, a quantum system briefly existed within before collapsing into whichever single, definite outcome we actually observe. There are several serious, competing answers to this question, each with its own dedicated community of physicists and philosophers of science who consider it the most physically sensible interpretation currently available, and it's worth walking through the major options honestly, because none of them has achieved anything resembling full, universal consensus, more than a century after the puzzle was first raised. The interpretation most commonly taught in introductory physics courses, sometimes called the Copenhagen interpretation after the city where several of quantum mechanics' founding physicists worked through its early mathematical framework, essentially takes the collapse of the wave function at face value, treating it as a genuine, fundamental, irreducible feature of physical reality, an actual, instantaneous transition from a mixture of possibilities into a single, definite outcome, occurring the moment a measurement takes place, without offering any further, deeper mechanical explanation for why or how that transition physically happens. Many working physicists, particularly those focused primarily on the practical, predictive power of quantum mechanics equations rather than its deeper philosophical implications, are content to treat collapse this way, using the mathematics to calculate accurate probabilities without necessarily committing to a specific, detailed story about what collapse actually is physically at the deepest level. A considerably more radical alternative, first proposed seriously in the 1950s and steadily gaining support among a meaningful portion of theoretical physicists in the decades since, rejects the idea of collapse entirely. Known as the many worlds interpretation, this view proposes that a quantum system genuinely never collapses into a single outcome at all. Instead, every possible outcome a measurement could produce actually occurs, each one unfolding within its own separate, subsequently non-interacting branch of reality, the universe itself continuously splitting, at every single quantum measurement occurring anywhere, into multiple, equally real, parallel versions, one for each possible outcome. Under this view, the reason we only ever experience one single, definite outcome for any given measurement is not because the other possibilities failed to happen, but because we ourselves, as physical observers embedded within one particular branch, simply have no access to the other branches, each of which continues on, entirely real, entirely populated by its own version of everyone and everything, permanently separated from ours by the sheer, overwhelming complexity of decoherence itself, which the many worlds interpretation reinterprets not as a collapse into a single outcome, but as the mechanism by which these separate branches lose all further ability to interact or interfere with each other once they've split apart. A third, quieter, considerably less discussed alternative, called pilot wave theory, or sometimes de Broglie-Bohm theory after the two physicists most responsible for developing it, takes yet another approach entirely, proposing that particles always possess definite, genuine positions and properties, at every moment, contrary to the standard quantum mechanical picture, but that their motion is guided, continuously, by an underlying wave, spread throughout space, that genuinely does exhibit all the strange interference behavior standard quantum mechanics describes. Under this view, a particle passing through the double-slit apparatus genuinely does travel through only one specific slit, at every moment possessing a real, definite trajectory, but the invisible guiding wave associated with it passes through both slits simultaneously, and it's the interference of that underlying wave that shapes where the particle is ultimately guided to land, reproducing the exact same statistical interference pattern standard quantum mechanics predicts, without ever requiring the particle itself to exist in some strange, ill-defined state of being in two places at once. Each of these three interpretations, Copenhagen, many worlds, and pilot wave theory, alongside several additional, less widely discussed alternatives that exist within the broader field, makes exactly the same testable predictions about the outcomes of any experiment physicists have currently devised the technology to actually perform. This is precisely why the debate over which interpretation correctly describes physical reality has remained genuinely unresolved for the better part of a century, not because physicists have failed to test the question rigorously, but because the different interpretations, despite describing wildly different underlying pictures of physical reality, one in which collapse is a genuine, irreducible mystery, one in which the universe endlessly splits into countless parallel branches, and one in which particles secretly possess definite trajectories the entire time, all agree, with total mathematical precision, on exactly what any given experiment should actually measure and observe. The disagreement lives entirely in the deeper, harder-to-test question of what is actually happening, physically, underneath those shared, agreed-upon predictions, a question philosophers of physics sometimes describe as being less about physics itself than about which underlying picture of reality a given physicist finds personally, intellectually, most satisfying to hold. Quantum computers have begun to offer, for the very first time, a genuinely new angle on this otherwise stubbornly unresolvable debate, not by directly proving one interpretation correct and the others wrong, a feat that remains, as far as anyone currently understands the mathematics, likely impossible given how carefully the different interpretations have been constructed to agree on every testable prediction, but by making the practical, hands-on management of decoherence and superposition an urgent, daily, engineering priority, rather than an abstract, purely philosophical curiosity. Researchers working on quantum error correction, the specific technical discipline devoted to protecting a quantum computer's fragile qubits from unwanted decoherence long enough to complete a useful computation, have developed an extraordinarily detailed, practical understanding of exactly how, and exactly how quickly, quantum superposition breaks down when a system interacts with its environment, understanding built not from abstract philosophical argument, but from millions of carefully measured, carefully repeated laboratory trials, run specifically to keep quantum computers working reliably enough to be commercially and scientifically useful. That hands-on, engineering-level understanding of decoherence has, somewhat unexpectedly, breathed considerable new life and new precision into the many worlds interpretation specifically, among a meaningful and growing portion of theoretical physicists working closely with quantum information theory. The mathematics quantum error correction researchers use daily to describe how and why decoherence causes different possible quantum outcomes to lose their ability to interfere with each other maps, with real and quite direct mathematical similarity, onto exactly the process many worlds theorists describe as separate branches of reality losing their ability to interact once they've split apart. Several prominent physicists working in quantum information theory and quantum computing research have become, over the past 2 decades, increasingly outspoken and increasingly technically detailed proponents of the many worlds interpretation, specifically because their daily, practical, hands-on work with decoherence in real quantum processors has given them an unusually intimate, unusually precise familiarity with exactly the mathematical machinery many worlds theory relies on to describe how and why parallel branches of reality would, if they genuinely exist, become permanently unable to detect or interact with each other. None of this constitutes proof that many worlds, rather than Copenhagen collapse or pilot wave theory, or any of the other available interpretations, correctly describes the deepest underlying nature of physical reality. It's worth being genuinely careful and honest about that, in exactly the same way earlier threads tonight required real care about not overstating what a given experimental result actually demonstrates. What it does represent is something more subtle, but arguably just as significant, a striking, unusual case in modern physics where an intensely practical, commercially motivated engineering effort, the daily grind of trying to build increasingly powerful, increasingly reliable quantum computers, has ended up generating genuinely new insight into one of the oldest, deepest, most stubbornly philosophical questions physics has ever raised. Insight arriving not from a dedicated experiment specifically designed to test the question, but as an unexpected, almost accidental byproduct of engineers and physicists simply trying to get their machines to work properly. That pattern, insight into reality's deepest nature arriving sideways, as an unplanned consequence of practical, applied research rather than dedicated theoretical investigation, connects directly back to where this whole evening's story actually began, with a small team of researchers trying to build a workable model of a wormhole using nothing but entangled qubits on an ordinary quantum processor, not because they set out specifically to prove or disprove any particular philosophical interpretation of quantum mechanics, but because they wanted to see whether a genuinely new kind of computational tool, one built from the same strange quantum ingredients the universe itself apparently runs on, could offer a genuinely new way of testing ideas that had, for decades, seemed permanently confined to abstract mathematics and careful theoretical argument, with no available laboratory technique capable of examining them directly. That desire to find some genuinely new laboratory technique capable of examining questions that had seemed permanently locked away in pure theory, connects every single thread we've followed across this entire evening into a single, coherent shape, one worth walking through slowly, one final time, before we let the whole picture settle. It began with two papers, written by the same physicist, published only months apart in 1935, describing what appeared to be two entirely unrelated strange features of the universe: a bridge through spacetime on one hand, and an uncomfortable, instantaneous correlation between distant particles on the other. For nearly 80 years, these two ideas sat in separate corners of physics, studied by separate communities, connected by nothing more than the coincidence of having been discovered by the same person in the same remarkable year. Then, in 2013, a mathematical argument proposed that these two strange phenomena might actually be the very same thing, wearing two different disguises: gravity's geometry and quantum mechanics' entanglement secretly describing one single, unified underlying reality. And in 2022, a quantum computer, a machine built from the same strange quantum ingredients Einstein found so troubling in his own EPR paper, became the first laboratory instrument in history capable of testing even a small, simplified slice of that audacious, decades-old conjecture directly. That same machine, and others like it, running on the very same underlying quantum principles, have simultaneously offered physicists an entirely new, hands-on window into a puzzle first raised more than 2 centuries earlier, when a single beam of light passing through two narrow slits revealed that the universe's smallest building blocks refused to behave like the small, definite, solid objects our everyday intuition insists they should be. The practical, daily struggle to keep a quantum computer's fragile qubits intact long enough to compute anything useful at all has given researchers an unusually precise, unusually detailed understanding of decoherence, the process by which that strange, superposed quantum behavior gives way to the ordinary, solid, definite world we actually experience. Insight that has, almost as an unplanned side effect, breathed new mathematical precision into one of the oldest, strangest, most genuinely unresolved debates in the entire history of science: the question of whether the universe, every time a measurement occurs anywhere, quietly splits into countless separate, equally real, parallel versions of itself, each one carrying its own copy of everything and everyone, forever unable to detect or interact with any of the others. None of these threads has fully resolved. That's worth stating plainly, one final time, because it would be dishonest to end this particular story pretending otherwise. The ER equals EPR conjecture remains a serious, actively studied theoretical proposal, meaningfully strengthened by that small, carefully qualified quantum computer experiment, but not proven, and not yet universally accepted throughout the physics community. The measurement problem, the deep question of what actually happens physically when a quantum system superposition collapses into a single definite outcome, remains genuinely, honestly unresolved, with serious, technically sophisticated physicists continuing to disagree, sometimes passionately, over whether collapse is a fundamental feature of reality, an endless branching into parallel worlds, or something else entirely. A disagreement quantum computers have sharpened and enriched without actually settling. It's worth nomming, honestly, what researchers in this field actually expect to happen next, because the trajectory matters as much as the current state of things. Quantum processors are continuing to grow, steadily, in both the raw number of qubits they contain, and more importantly for this particular story, in how long those qubits can maintain coherence before environmental interaction destroys their delicate superposition. Each incremental improvement in that coherence time translates directly into an ability to simulate larger, more complex, more faithful quantum systems, meaning the small 9-qubit wormhole model discussed earlier tonight represents, by most researchers' own explicit acknowledgement, an early, deliberately simplified proof of concept rather than a finished, definitive experiment. Physicists working directly on this research have been candid in interviews and publications about their own roadmap, describing plans to scale these kinds of experiments toward increasingly faithful models of the ER equals EPR conjecture as hardware continues to improve, work that remains ongoing, active, and genuinely uncertain in its eventual outcome. Similarly, the practical work of quantum error correction, the daily engineering grind responsible for so much of the unexpected insight into decoherence, and the many worlds debate discussed a few minutes ago, continues advancing steadily, year over year, as companies and research institutions around the world compete to build increasingly large, increasingly stable quantum processors capable of maintaining useful superposition across hundreds, and eventually, researchers hope, thousands of qubits simultaneously. Each advance in that underlying engineering effort, largely motivated by entirely practical, commercial goals involving cryptography, materials science, and complex optimization problems far removed from anything resembling deep philosophical inquiry into the nature of reality, continues to generate, as an ongoing byproduct, an ever more detailed, ever more precise understanding of exactly how and why the quantum world's strangeness gives way to the ordinary world we actually inhabit. What has changed, genuinely and significantly, over the past decade is the nature of the tools available to keep working on these questions. For the better part of a century, anyone wanting to seriously investigate the deepest, strangest features of quantum reality was largely confined to either abstract mathematical argument, careful but limited tabletop optics experiments involving individual photons and delicate arrangements of mirrors and beam splitters, or patient theoretical work waiting for some future technology capable of testing ideas that current instruments simply couldn't reach. Quantum computers represent something genuinely new in that long history, not merely a faster calculator, but an entirely new kind of instrument, built directly from the same strange quantum substrate the deepest questions in physics are actually about, capable, for the first time, of directly constructing and manipulating the very phenomena, superposition, entanglement, decoherence, that earlier generations of physicists could only theorize about or glimpse indirectly through far more limited experimental means. There is something worth sitting with in these final few minutes about what it actually means for a species to have reached this particular point, capable of building a machine intricate enough and precise enough to directly probe questions about the fundamental nature of space, time, and reality itself. Questions that, for the overwhelming majority of human history, existed only as philosophy, myth, or pure abstract speculation, entirely disconnected from anything a person could actually build, measure, or test. The chip inside Google's quantum processor, cooled to a temperature colder than the depths of interstellar space, isolated from every stray vibration and every unwanted photon human engineering can currently manage to exclude, represents a genuinely new kind of achievement, not simply technological, though it is certainly that, but something closer to an extension of human curiosity itself, reaching directly into the strange, foundational machinery of the universe, and for the first time, actually touching it, manipulating it, watching it behave exactly the way the mathematics always said it should, however uncomfortable, however strange, however far removed from anything our ordinary, everyday intuition ever prepared us to expect. Thank you for spending this long, quiet evening with us here at Pale Blue Drift, tracing the strange, still unfolding story connecting two papers written 80 years apart, a beam of light passing through two narrow slits more than 2 centuries ago, and a small, carefully cooled quantum processor sitting in a laboratory today, quietly testing ideas about the fundamental fabric of reality that, until remarkably recently, nobody had any real way of examining directly at all. If slow, strange mysteries like this one, the kind that reach right down into the deepest, most foundational questions about what reality actually is, are the sort of thing that helps your own mind settle into something calm and curious before sleep, there will be more evenings like this one waiting for you, more careful uncertainties, more patient, unresolved questions, more long, unhurried nights built for exactly this kind of stillness. For now, let the rest of tonight be simple. Somewhere, in a laboratory kept colder than deep space, a chip built from the same strange quantum substance the entire universe is apparently made of continues sitting quietly, waiting for its next experiment. And somewhere else, in whatever room you happen to be resting in right now, your own body, built from trillions of atoms each individually obeying exactly the same strange quantum rules, has, through some process nobody fully understands yet, settled comfortably into the single, solid, definite version of reality you actually experience, breathing slowly, steadily, needing nothing more from tonight than the rest that comes next. Sleep well.